4.4, modeling and optimization. So in 4.3, we learned about min and max. Since 5 people literally like took the quiz today through extensions or sickness or whatever, I haven't graded the quiz yet because that's like a third of you. Cool. So that just means you'll get it back Thursday. I wanted to wait till everyone was done. I don't have you tomorrow. That's why Thursday. Not gonna lie, I'm not gonna have time to grade it tonight. So tomorrow I'll be grading it. Cool. All right. So 4.4, modeling and optimization. So 4.3 taught us how to find min and max. So do we remember how to find min and max? What was the steps? One person. Can you summarize it for us? Hannah.
You find the derivative.
Okay.
Set the derivative equal to 0.
Or undefined. Or undefined. Okay.
Or undefined.
Solve. Get critical points.
And then you plug those into a number line.
Mm-hmm.
And then you see if it's positive or negative to make the wave. And then you see if it like changes from positive to negative.
Yeah, so if we had a positive derivative that went to negative, what will we have? If we go from positive to negative?
A max.
A max. If we go from a negative to a positive, I'll wait. All right, so I'm reviewing right now. Technically, I have you guys not sitting next to each other. You could go and ask them to move. Literally just ask them to move. That's it. Okay. Because if I'm gonna let you stay there, I have to let the Hannahs sit next to each other, just to be fair. And just have them move. Okay, we're just gonna go through this. Let's go.
I did ask them, and they said so. That's why.
You said no?
They said
You said no?
And then I just said I'll just sit here.
Oh my gosh.
Like, okay. That's so pretty. I'm sorry.
It is. Okay, so we learned how to find max and mins. So now, guess what? We're going to optimize, right? So real world problems, we're going to use this min and max strategy to actually find the numbers that will help us. So for instance, let's say you're the, what is going on now?
Exactly.
Tall.
No, she just, that was my fault. I'm really sorry. Her nails were pretty.
Like literally, this is it. If you two screw up again, you're out of the class for the day. I am over it. We're learning the lesson, and like as much as I like you, I'll send you out because I'm over it right now. Okay, so min and max. Let's say you want to make a box. Well, you don't want the box to use a lot of material because that's going to waste a lot of money. So how do we make sure we have the maximum volume per surface area? I want to minimize like the cardboard I'm using to make my box and maximize like the volume. Okay, so how do you actually do this? First, we have to actually understand the problem, right? So you have to read the problem and say, okay, here's what I have, here's what I have, here's what I need. Right, so identify the information you need to solve the problem, then develop a mathematical model of the problem. This is probably one of the hardest parts, right? So you can draw a picture, label the parts that are important. That'll help, but really, the main thing I'm worried about is you guys being able to introduce a variable to represent the quantity to be maximized or minimized. So you're supposed to have everything in terms of one single variable. Okay, so for instance, if you're trying to find the volume of a box, right, you have the width, length, and height. Well, let's say we want everything in terms of width, right? So maybe you can rewrite the height as in terms of like 1/2 width or something, right? Everything has to be in terms of one single variable. And then using that variable, write a function, right? So this is the part you're probably going to struggle with, is being able to write it in one function, right? This is what I think. I think you'll have trouble with that. But once you find the function, guess what? You find the domain. So if I'm trying to find, okay, maximize the volume, minimize the surface area, well, think about length, width, height. They're never negative, right? So figuring out the domain, you have to use common sense. Determine which values make sense. Like you're not going to have a negative length, And if I have a sheet of metal that's only 20 feet long, like you can't have a length that's 21 because, right, like the constraints of our physical thing. And then it's what we have been doing. Identify the critical points, the endpoints, right? Find where the derivative is 0 or fails to exist. Solve the model. So if I'm trying to maximize profit, well, okay, where is my profit the highest? You use like your max or your mins. That's normally where we're going to be using it. Interpret the solution. So for example, I'm sorry, I'll go back. For example, length can't be negative. So interpret the system, the solution. So use the DIMS test. Does it make sense? Does it make sense? That's the DIMS test. So at the end, you just have to make sure it makes sense. Okay. Do you have the notes packet? Did you get it from? Okay, you got it. Okay. So example 1. So this is, you can solve this yourself. Guess and check. What? No. Well, I didn't say two distinct. Yeah. Trick play. So this one you can figure out like just guessing and checking, but we're going to go through the method. Maya, if you need to go get a drink of water, it's fine. Yeah. All right. So
that means two different numbers?
What?
Would this question imply?
Did I say find two distinct numbers? No, I just said find two numbers. So it just has to be two numbers, 10 and 10. I don't like the look you're giving me, but whatever. All right, so, you know, this is an easier question than what they used to do. This makes more sense because it's gently guiding you into this, like, strategy for solving instead of just going off the deep end and using, like, hard problems. Because you could, like, come up with it yourself. Okay, two numbers whose sum they add to 20 and whose product multiply largest possible. So let's let the first number be x, right? X is normally the variable we're going to use. So let x equal the first number. Okay. So I could say I could have like y be my second number, and together x plus y has to equal 20. Let me write that a little smaller. I'm just gonna have like y be my second number. Y is second number, and together they sum add to 20. And we want the product to be as large as possible. So if I take x times y, I want to maximize this. Okay, so we understand the problem. We want to have two numbers. We want them to add to 20 and have a product multiply together as big as possible. Okay, we want to identify a mathematical model. Okay, so it's not really a picture to draw for this. It's not like a box or anything. But we do need to have a variable represent the quantity to be maximized. So I only want one. Everything has to be in terms of one variable. How can I get the second number in terms of my first? Any idea? How can I get the second number in terms of my first? Yeah, exactly. Just subtract. I'm going to move this down. Oh my god, so slow. Move this down a little bit. Okay. So if oh, that was the wrong way. X plus y equals 20. If I want to get x by itself, you just subtract y from both sides. So I see x is equal to 20 minus y. So what I'm trying to maximize, is x times y. Well, y was, we just said 20 minus y. 20 minus x. Oh my god. I solved it the wrong way. I was supposed to subtract x. Sorry. Because I want it in terms of y. I'm sorry, I want it in terms of x. Solve for y in terms of x. I can't even talk right now. So this is what I'm trying to maximize. I'm trying to maximize this x times 20 minus x. Okay, secretly this is x times y. All right, x is my first number, y is my second. Add them to equal 20. Multiply them, it's as big as possible. So our second number, so first number, x, second number, 20 minus x.
So essentially you try and get y on one side and x on the other?
Well, I have y solved only in terms of x and numbers.
Okay.
Yeah, because now I have this whole thing and it's only in terms of x, there's no y. Okay, so I have a function, right? That was step 2, develop a mathematical model of the problem. Using the variable, write a function. Check. Step 3, graph it, find the domain. Okay, so what's really our domain? So secretly, this is a quadratic, right? Quadratic's domain are all real numbers. But for our problem, really, what's the domain? Between what two numbers? Yeah. We're probably not going to include, 0 and 20. It's probably not our answers, but we can include the endpoints. But if I add 0 and 20, okay, it's 20, but if I multiply them at 0, it's probably not the biggest number I could get. But think about if I said like, oh, what about -1 and 21? Those add to 20. But remember, we're trying to maximize the product. For multiplying by a negative, it's small, so it's below 0. Okay, so really our domain is between 0 and 20. So we just need to find, we have to maximize, we have to find where is this function the biggest between 0 and 20. How can I find a maximum? It's the first thing we talked about today. Review of 4.3. Find the derivative. Okay, let's find the derivative. So let me, what?
You said I just feel this takes so much longer than like.
So the reason we're doing this is to prepare you for the next problem where we have to apply the same strategy. Yes, this was an easy problem. Next time I'll make sure to poke you with a really hard problem that you cannot solve another way. You know, like I'm trying to have a problem where it's like, okay, you know the answer, like, you know, I'm showing you a new way to prove to you that it works.
So
Okay.
are we making f of x?
I want to maximize f of x. So I'm going to take the derivative of f of x. So the derivative is going to be 20 minus 2x.
What would have happened if you did the formula?
I mean, it's just way easier. It's the same answer. Yeah, you get the exact same answer. Product rule. Because it's 1 times 20 minus x plus negative 1 times x. Yeah. Okay, so we want to maximize this. So we want to find the critical point. So I'm going to factor. We must factor this.
Oh, because
Pull out a 2, 10 minus x. This is the only thing that'll give me an answer. The 10 minus x will be the only thing that gives me an answer. Set it equal to 0. I see my critical point is at x equals 10. So x has to be 10. Remember, how do I find y? 20 minus x. Yeah, let's plug it back in. 20 minus 10 is 10. Oh, so my numbers are literally 10 and 10. These are the two numbers. Add them, you get 20, and multiply them, you get 100. Right, so Spencer first was like, oh, 9 and 11. Yeah, well, okay, that adds to 20. Multiplies to 99. 100 is more than 99. Trick play. If I said two distinct numbers, yeah, it didn't say two distinct, two different. It just said two numbers. Well, they have the same number.
what happens if it says two distinct numbers?
It would be different,
How
which I did not specify that. I didn't specify in this problem. And I don't want to confuse you right now, so I'm going to focus just on this, just so we can get to the next problem. Yeah. I'm not answering that question. I'm not going to answer if it said two distinct. I'll answer it next time. Maybe. We'll see. I just want to get through this lesson today. That's it. Right? So let's see the forest, not a single tree. Okay? Don't get caught on a branch. I want you to understand the method. So we have a critical point at 10. So to confirm, we're going to confirm, this is how I'm going to do it. All right, so I know I'm going from 0 to 20. And I have a critical point at 10. So if I plug into this guy right here, a number between 0 and 10, how about 5? Will this give me a positive or negative? Positive. And if I plug in 15, will this give me positive or negative? Negative. Okay, so that means I'm coming up, going down. Maybe I should pick a different color to show you that this is my function, my derivative, and then this guy is going to be my function. So I'm coming up, coming down. I have a max at 10. It proves it. All right, questions over this one? Pretty straightforward. We only have 2 more examples, but it will probably take the rest of class. So I know this is, I don't know, I'm hoping this won't be hard. I think the hardest part is actually finding the function, like writing the function yourself in terms of a single variable. So first, example 2. Let's understand the problem. An open top box is made by cutting squares of side length x from the corners of a 10 by 16 sheet of tin and bending up the sides. All right, so you have a square sheet, you cut out corners just like it's shown, and then you bend up the sides to make an open top box. It's kind of like a Krispy Kreme box, right, like the bottom. So how large should the squares be to have the box hold as much as possible? What's the resulting maximum volume? So we want to maximize volume, but we only have this sheet, right? It's solid 10 by 16. That's it. That's all you get. That's all the metal you get. We want to maximize the volume, all right? So we want to know I want to have as many Krispy Kreme donuts in there as possible, right? I want to maximize the volume. So we have a picture drawn for us, so let's try to understand the problem a little better. So we're cutting, what does it say? We are cutting squares of side length x from the corners, okay? So I come up here, this length is going to be x, this length is x, this length is x, this length is x. So I'm cutting squares, x by x.
Is 10 by 16
The whole sheet.
So with, like, excluding the pieces cut out?
So this whole length is 10, this whole length is 16. So exactly, oh my gosh, so guess what? So what's this length right here? What is this guy's length?
16 minus 2.
Exactly, 16 minus 2x. And then this length is just going to be 10 minus 2x. Okay. Because secretly, you know, this was a rectangular piece of tin. We cut out the corners. And we're going to bend the sides up into an open top box. Okay. So, I'm not the greatest artist, I'm just going to warn you, but I'm going to draw a, like, representation of an open top box.
Shoebox.
Yeah, it's like a shoebox.
That was a really good job.
People assume I am because I teach math.
That's a horrible.
I also think I can't, like, write or speak or do English. Whatever.
That makes no sense.
I don't know, it's just like, literally, it feels like people stabbing me every time I'm like, oh, I tutor SAT, and they're like, oh, just math? Sorry, you're dumb, like, whatever. Okay, I'm over it, I'm good now. Alright, I gotta focus. I can't be so angry all the time. Just want you to be successful. I also want to make money. Okay. So, ready? So you take this top sheet, ready, and bend it up. So this is the 3D open top box. So let's talk about the length. Okay, first things, maybe I should have drawn this a little different. I'll have this side, since it's longer, be 16 minus 2x. This length is 10 minus 2x. And what's the height of my box? X, exactly. Ooh, okay. So we have our sheet. We have the open top box. Now, remember, what we're trying to find the resulting maximum volume. We have the maximum volume, okay? Max volume. How do you find volume? And I'm not going to be giving this equation to you because I believe in you. I probably have a little too much faith. Length times width times height. Okay, wonderful. So our volume is length times width times height. Oh my gosh, look, we have everything in terms of one variable, x. One more time. We have everything in terms of one variable, x. Oh my gosh. Okay. So it's fine.
It's open.
Yes. I'm not talking about surface area, I'm talking about volume. I don't care if I have a lid or not, it still has the same amount of volume, not like 3D space inside. But
the more you cut off the sides, the less you're gonna have of the height.
That's why it's asking how long.
we're trying to maximize. Trying to find. So, right, the more I cut off, the higher I have, but the smaller, like, the dimensions of the base. What?
This is engineering and architecture.
No, I mean, yeah, okay, I guess I could see it. Okay, so length is 16 minus 2x. Our width, 10 minus 2x, and our height is just x. Cool. Can we write this? Do a little better. Can we FOIL two binomials by each other?
We can.
Yeah, exactly, you can. Yeah, you can do it. So 16 times 10, so that's 160. Let's see, minus 20 minus 16, so minus 42x. No, 52. 20 and 30, yeah, minus 52x. Plus 4x squared. And then I still have an x on the outside. All I did was I FOILed the two binomials. Okay, let's distribute that x out. Are we good how I found this? Okay, I believe that you can FOIL it. You guys can do it. Okay, I found my volume. Bless. This is the equation to find volume. So we could like test a bunch of values, right? What if I don't cut any? Aha, I don't cut any, no squares, right? X equals 0. Whoa, turns out our volume's 0, which makes sense because it's just flat. There's no height. What if I cut like, I don't know, 2 inches off, 3 inches, 5 inches? Ooh.
Well, how do you know?
Starts talking about our domain. Do we know what our domain should be? So, right, or it has to be greater than 0 because you can't cut negative distance, right? It doesn't make sense.
So 16. Doesn't have to be less than 8.
So let's think about it. X is the amount that we're cutting off, right? X is the amount that we're cutting off. So think about it. If I cut 1, right, 1 inch off, right, 1 inch, that means this side length would be 8, right? Because 10 minus 2 times 1, 10 minus 2 is 8. But if I cut 3 inches, 10 minus 6 is 4. Oh, what's the maximum amount? What's the max X can be? 5. Because if you're cutting 5, oh, you're literally cutting this whole chunk off, right? Because you're 5 from both sides. Oh, you literally cut the whole thing off.
But what about your...
So 5 is the largest it can be.
What if you look at the other side first and said 8?
Well, this is smaller though. This is the smaller
So
side.
you just write
If I pick
the
8, this would be negative. No, I only have a single domain. If I pick 8, well, 10 minus 16 is negative 6. We can't have it be negative. Can't have a length be negative. Yeah. So that's why it's 0 to 5. Okay, so our domain 0 to 5. Wrote words of encouragement on the board. I told you it was going to be hard, but we can do it just like together, okay? You can sigh, just not audibly, because it will literally break my heart. Please, just focus.
Me?
Yes.
No, I'm totally focused.
Okay. Our domain 0 to 5, right? If we don't cut any of it, that would be 0 volume. If we cut 5, well, I mean, literally I'm cutting my whole bottom off because 5 from both sides takes away all 10. So we know it's not going to be either end. Like, you know it's not going to be 0 because that's 0 volume. You know it won't be 5, but that's our domain. Like, it really, we shouldn't include it because we know it won't be the end. Okay. So we want to maximize the volume, okay? We want to make it as big as possible, maximize. How do we find maximum? Elliot?
You multiply, you find the volume of that, and then you find the derivative.
Derivative, perfect. Let's take the derivative.
12x squared minus, 104x.
Okay, yeah, let's make it a little easier. I'll rewrite it. Let's see. 12x squared minus 104x plus 160. Oh my gosh. Can we, like, I don't know. Remember how to find max and min? We take the derivative, set the derivative equal to 0 or undefined. So literally I need to factor this. Is there, like, first thing. It's the easiest thing I can do. Pull, it's really, that'll take a long time. Take out, not everything, 104 is not divisible by 12.
Take out a
4.
Take out a 6.
Take out a 4. Yeah. 3x squared minus 26 plus 40. And then that's a little easier to factor. Right? So I want to set my derivative equal to 0 to find, because we're maximizing. So I just need to factor 3x squared minus 26x plus 40. 3x minus 20. And x minus 2. We could like do it on the side. Like, this is yeah, if you have trouble with the factor, just come into bonus. Like, we'll do it. Okay, so we gotta set equal to 0. So set each factor equal to 0. This one gives me x equals 20 over 3. What's 20 over 3 roughly? 6.66 or so, right? 6 point something. 6 point something, is that in our domain? No, not in our domain. Goodbye, not in domain.
How did you find that the domain was to 5?
Because the one side that's 10, I only can cut 5 from both sides before I'm like out of things to cut. Right here, I only can cut at most 5 from both sides because that's where I meet in the middle and slice. Because the whole length is 10.
Oh, okay.
Yeah, because I don't want my length. If I get like anything more than 5, 10 minus 2 times 5.5 or something gives me a negative number. I can't have it be negative. Okay, so I see x equals 2. So we can check it, okay? We can check it. I can draw a number line. All right, so I'm going from 0 to 5. Here's my 2. If I plug in a number like 1 into... don't want to do it that guy. I could do it to this one. Plug in like 1. I get a negative times a negative, so that's going to be positive. And if I plug in a number like 3 into this one, it will be negative. So, turns out, it comes up, then it goes down. So this is where my max occurs, is at 2. So the squares, right, these squares we're cutting out of the tin should be 2 by 2, 2 inches by 2 inches. That's what this is saying. That's what this is saying right here, where we found x equals 2. That told us how far in we should cut. So these little squares we're cutting away from our sheet of tin, they have to be 2 inches by 2 inches. Okay, so how large should the squares be? How large should the squares be to make the box hold as much as possible? Boom, found it. 2 by 2. Second question, yeah, 2 inches by 2 inches. Yeah, because if x is 2 and we're cutting out squares, if one side's 2 and it's a square, it means the other side has to be 2 as well.
Oh, because it's a square.
Yeah. Okay, so check. We found the dimensions of the box, the square. Now, what is the resulting maximum volume?
72, 74.
So let's plug straight into this guy. All right, V of 2 is going to be 16 minus 4 times 10 minus 4 times 2. 16 minus 4 is 12 times 6 times 2, so it's 144. 144 inches cubed, because it's a volume, cubed. I'll pause here for a moment. Yeah. It is. I'm not gonna lie. I tried to kind of preface and told you this is gonna be a hard chapter. You really have to think. You have to think about things, really understand the problem. You have to be able to read English, word problem, understand, comprehend, break it down. This is where we struggled. When I taught physics, this is where people struggled. They see a word problem, they shut down. But it's just figure out, what do we know? What's given to us? What are we trying to find? Put everything in terms of one variable. And then it's just going into 4.3, minimizing, maximizing, yes.
So why did we not have to do the whole thing with the x and y, where you have to make it into is it?
We did, well, everything was in terms of one variable already. Everything was terms of x, so I didn't have to change anything around.
So what if
right?
it was x was 1 and y was 2? That's a much harder problem. So then you have
because we'd have to have some relation between, if this was x, if we're cutting vertically by x and length by y, you'd have to have some relation that relates these two. Because you'd have as many equations as you do unknowns. So here they only gave us one piece of information that they were cutting out squares, but each side was x. Okay, that's all we really know. Everything was in terms of x, so we're good. Right? Volume, length, width, times height, everything's in x, so we go. This next one is a little harder because it's something in terms of x and y, right? So it's kind of I see how it makes sense for you, right? It's a logical next step. What if not everything's in terms of x?
It's in terms of
so, okay, so just so you're aware, we don't have class tomorrow, but Thursday is the second day of 4.4, and I have a worksheet for us to do. We're gonna have more practice. Yes, more practice. It's all good. Just more practice. It's just a way of thinking about it. And they're long problems. It's tiring for your brain. But these are also the most real world. Yeah. Okay. Are we ready? Okay. It's kind of like the difference between example 1 and 2. That step up is how this steps up. So first, let's just read the problem, understand what the heck is going on here, okay? So example 3, a rectangle is to be inscribed under the curve y equals square root 9 minus x squared. What are the dimensions of the rectangle with the largest area, and what is that largest area? Okay, so a couple things. What does it mean to be inscribed? This problem's not going to be, if we don't even know what the word means, it's going to be rough. What does inscribed mean? Inside, right? Inscribed, you are inside. Inscribed is inside. Okay, so inscribed means it's literally inside. All right, so that means the corners of my rectangle is going to be inside the half circle. Did I cover that? That this is a semicircle? No, I don't think I said that. How do I know it's a semicircle?
Domain.
Because it can't be 0.
It's the square root.
Yeah.
It's a square root. Yeah. Of a and a square and a. It's just gonna be a square root. Because if you think about when you studied equations of circles, x squared plus y squared equals, if I say like 1, and you're trying to solve for y, okay, well that means y squared equals 1 minus x squared. You don't have to write this. But just explaining how I know it's going to be a semicircle. Like it's in the form number minus x squared under square root. So this is from conics. I think you did that I think you learned this in geometry? Yay, nay? Yeah? No? Yeah? Yeah? Okay, I don't know. But this is a semicircle. Cool. Right? This is just a semicircle. If you graph it, because you will have calculators, it's literally just a semicircle. And it's graphed for you. Surprise! This is a semicircle. Okay. So, inscribed under this semicircle. The rectangle's inside the semicircle. And the corners are going to be on the semicircle, right? The corners touch the semicircle. So, inscribed is inside. And since we're having a rectangle, that means the corners will touch. Touch. And inscribed is inside, literally. Okay, so my rectangle could look something like this, right? Because the corners touch. What is the width of my rectangle? Do we know what this length is right here?
Yeah.
Yeah, it's just x. So if this length is just x, the whole length across will be 2x, exactly. Because it's not, right? So the distance from the origin to this point is exactly our x value, like 2.5. So the length totally across is 2 times that.
But why does it have to be from your like you didn't have the
It's on the origin. It's like from the origin. Yeah, we're centered around 0. Like, I want to know the total length. If I said this length is x, like, no, it's not. This x value here is 2.3. Because think about how will I find the height? What's the height? I think that'll make more sense. If we talk about the height, you'll see why.
Talk about the height. The height is from
The height is literally this function value. And we know the height because we know that function value. The function value is square root of 9 minus x squared. Right? So the curve is literally your y. The curve is your height. So I need to know, okay, at a certain x, what is my height? Because it depends where we are, right? The x value, we have to plug it in to find the height. That's why I can't just have the width be the x value. Yeah. Okay, so this height is y. Well, we know y is 9, square root of 9 minus x squared. This is the height, and it's going to be square root of 9 minus x squared. What? Okay.
Why did you decide to draw the height at 2.5?
Okay. So I see what you're asking. That was like the next thing I was going to talk about was what if my rectangle wasn't there? What if instead I drew my rectangle right here? Well, still, at this point, right, this height, it's still, okay, so whatever x value I'm at, let's say 1, I need to make this actually be a rectangle. So if I'm going to draw, okay. That's better. So my two corners of the rectangle touch my semicircle. So still, this x value where I'm at, x equals 1, the total width would be 2 times that, which would be 2. My height here, well, I find the y value by plugging into the equation, right? Square root of 9 minus x squared. That didn't answer your question. So, right, so there's many, many rectangles we can draw. What we're trying to find is which rectangle will give me the most area. I don't know, I haven't drawn it yet. I could draw a rectangle that looks like this. That's what we're trying to find. We're trying to find the x value so I can like draw my rectangle and then come up for the maximum area.
What if they'll all be the same?
They won't. Surprise. Okay. So the semicircle is literally the height of your rectangle, just so we're aware. This is how we find height. I know it seems like it, but it won't be. Just the two examples I have. What is 5 times 1.5? 7.5. So the red area is 7.5. Now let's try this one. What is 2 times 2.8? Definitely less than 7.5. Right? Yeah? Okay, let's try the purple one. 2, okay, so it's 4, so I have to double 4 times 2.1. Oh, that's 8.1. Okay, so we're getting closer, right? This purple one so far was the biggest area. They all have different areas. We're trying to maximize the area. Like, I know, oh my god, everyone's gonna get lost with it. It's okay, because we're gonna get through this one. We'll start on the worksheet. We'll finish the worksheet tomorrow. Just more practice and you'll understand like the process, right? The first time you ever shot a free throw correctly, you have no clue what you're doing. Takes lots of practice.
I still don't know what I'm
You're not gonna be the Michael Jordan of math in one day. Like, come on. You know, think about when you learned how to walk. Did you just all of a sudden stand up and start walking? No, you definitely fell flat on your face, right? Like, we gotta do this. Oh, I guess Spencer didn't. Okay.
I'm just saying, I'd like to see the video.
Oh, to me?
No, for me.
Oh, that'd be great.
It's so fun.
Should bring it. Okay, question.
Sorry. If you were to draw like any of those rectangles, you would write the same
Yes.
x and y. So
Yes.
how would you get it?
Because it depends which x we're at. So the ones I drew, like I was like, oh, I'm at x equals 2. I'm at x equals whatever. But so I was trying to like give you some examples. Because imagine like numerically, like with your calculator, you could go through and start at 0 and go by 1/1000 and literally figure out what it is. That's numerical. Like it's, so that's how, I don't want to like get into it. Okay. There's like some math where you like use numerical methods. We're trying to like take a shortcut. Let's apply what we already learned. We know we want to maximize x. We're going to write everything in terms of x. We're going to maximize it and see at which value gives us the biggest area. Okay, so we're trying to find the area. How do you find area of a rectangle? Beautiful. Base times height. It's triangle 1/2.
I know.
Okay, so let's think. My base, we just said, was 2x. And my height, square root 9 minus x squared. So this is my area. So if I graph this, like, cool, I want to see where is my area the biggest. And then at whichever x value that occurs, that will be like the x I plug in here. Maybe for my previous problem example too, I should have graphed that cubic function and you would see like where it hits a maximum between 0 and 5. So okay, this is the equation of my area. What's our domain?
Oh no. 3 less. 0 to 3.
0 to 3, yeah, 0 to 3. Why is it 0 to 3?
Would it not be 3?
What? Why is it 0 to 3?
To get x.
Yeah, from the origin to like our right point, because we know it's just going to be like reflected across. Okay, so all I'm going to do is I'm just going to rewrite my area in terms of something that will help us take the derivative a little easier. So 2x times 9 minus x squared to the 1/2 power. Now we get to use what Tal wanted to before. We're going to use the product rule to find our derivative. So before I write that, let's have this be u, and this is v. So I'll pause here and make sure we're all together when I'm finding v prime. Okay, so I'm going to use the power rule, bring down the 1/2. Rewrite the inside, minus 1, okay, so it's the negative 1/2, and then times the derivative of what's inside, so times negative 2x. I really hope I don't get the flu. My friend.
You got a flu shot?
No.
Go after school.
My friend who I saw on Sunday now has the flu, so.
Go get a flu shot now.
But
Like
if
after
she's
school.
already-
After school.
You have a game.
After that, go to urgent, like the pharmacy, they have it, but also like.
Then Ty has a game after that. What? Then I have a tutoring client. That's why I said I probably won't have time to grade your stuff tonight. It'll be tomorrow. Yes, Elliot.
I read this thing about the flu shot,
Oh gosh.
and I was thinking, so it's like the actual thing that's like in you or whatever, it has like a coating, and during the winter, it's like heat sensitive, so the coating like cools. So that's why the flu season's in the winter, because it doesn't like protect you.
Causation versus correlation. If you think about the cold, people are inside and a lot more proximity during winter.
That too, but also what I said.
I mean, it's
Sure.
California. People
Okay, let's make sure we understand this.
Google.
Elliot,
So-
I think it's really interesting.
I think it's interesting to jump in front of Elliot. He's smart enough.
I hear you. It's just a question of causation versus correlation. Okay, ready? 1/2. Bring it down. Subtract 1, so negative 1/2. Ooh, to chain rule, so we gotta take negative x squared derivative, which is negative 2x. 1/2 and 2 cancel out. Sum of negative x times 9 minus x squared. So 1/2, negative 1/2. Okay, goodie. Yeah, throw back to me. You thought this was hard. JK, let's keep going. Right? Hey, okay. So remember what we're doing? Product rules. So I'm gonna do the product. Let's write out the product. Don't you feel like you're getting your money's worth now? Hello, math, where you're like,
It's my mom, my parents' money.
okay, okay,
It was a joke.
not funny. Okay.
Everybody tells me I'm not funny. I think I'm the funniest person.
Okay. So
Everybody tells me I'm not funny.
u prime times v. U prime times v. So 2 times 9 minus x squared to the 1/2 power plus u, which is 2x, times v prime. What?
Oh, you just like cancel. What is your negative?
What?
What is your negative? What is your negative?
So u prime v u. And this is v prime. Sure, in the intermediate. So you could do this whole thing first. Commutative property of addition, because you're adding, doesn't matter the order you add. Yeah. Okay, let's just simplify this just a little. So 2 times 9 minus x squared to the 1/2 minus 2x squared times 9 minus x squared to the negative 1/2. Make that a little bigger so it's easier to see. Think about, is there a common factor we can pull out? I think in chapter 3, the trick I'm about to show you, I showed you then. There's like a 9 minus x squared, right? But one of them's to the 1/2, the other's to the negative 1/2.
They just cancel out.
Not quite. What if I pull out? What?
What if you pull out the 9 minus x
Either,
squared
but
to the
either
power?
way, don't you end up with
I'm gonna pull out. I'm gonna pull out a 9 minus x squared to the negative 1/2 power. So what I'm left with is 2. Okay, if I'm pulling out this, I have 1/2 minus. 1/2 minus a negative 1/2. So that's actually adding 1. So this just turns into 9 minus x squared to the first power, and then minus 2x squared. Do you want me to show you how I did that?
No, I got it.
Okay, let me do it this way. If I have x to the 1/2 minus, let me have an actual number, like 2x to the negative 1/2. Okay, so I'm pulling out a negative 1/2. So it's literally like I'm dividing by a negative 1/2, x to the negative 1/2 power. So this guy goes away. That's why I don't have anything right here, because this totally went away because I pulled it out. Okay, this other one, how do I figure out what the exponent should be? 1/2 minus a negative 1/2, same as plus a half. 1/2 plus a half is 1. That's why I have an exponent of 1 right here. Yeah? Yeah? Okay. Okay, so we're good. Mostly. Guess what? This whole inside is polynomial-ish, right? Just algebra. Just do the algebra. So I'm going to write this as 9 minus x squared to negative 1/2 times 18 minus 4x squared. We're almost there. Almost there. I have a negative exponent. One more step of simplification. So this is 18 minus 4x squared over 9 minus x squared to the 1/2 power. Okay, and that's where we'll leave the derivative, okay? Now we got the derivative, it's fully simplified. We're good to go on to 4.3, which is just min and max. How do we find critical points?
Equal to 0.
Or undefined.
Undefined.
Okay.
Would you rather us make it a square root or leave it as a...
You can leave it as a half. It's fine. It's probably a little clearer if you leave it as a half, because the square root people have dropped in the past. Yeah. Okay. So, finally have the derivative. That was the rough part, right? Coming up with the equation and derivative. Oh my gosh. And now we just have to see, okay, where is it equal to 0? So I'm looking for where our derivative is equal to 0. Well, when is 18 minus 4x squared equal to 0?
Oh, wait. Sorry.
So 18 over 4. Okay. So 18 equals 4x squared. Oh my gosh, I can't even write. Divide by 4, so I have 9 over 2 equals x squared. Square root both sides, so I have the square root of 9 over 2 plus or minus equals x. So it's just plus or minus 3 over root 2.
Whoa.
Okay, so I'm going to cross something out, but I want to make sure we're like good before I cross it out. Think about what our domain is. Can it be negative? No, we only can have like positive side lengths. Remember, our domain's from 0 to 3. So a critical point is at 3 over root 2, right? So we have a critical point at x equals 3 over root 2. That's one way to find a critical point, where it's equal to 0. The second way is where it's undefined, right? So f prime is undefined when this bottom equals 0. So what would make the bottom equal to 0? Yeah, when x is equal to plus or minus 3. Well, we know it can't be negative. Can it be positive 3? Because that would mean our rectangle has 0 height. so it can't be either one of these. Remember, a domain is from 0 to 3 with not inclusive, so that can't actually equal 3. So we found our one place. We found our x value. We found our x value, right? X is 3 over root 2. Almost there. I have like a minute more of work, but that's it. So, throwback. What is the actual first question we're trying to solve? What's the first thing we're trying to solve? What are the dimensions of the rectangle? Oh, so this gives me what the x value is, not what our dimensions are.
Oh.
So I have to find the dimensions. Okay, dimensions. So our base, we said it was just 2x, right? So it's just 2 times x. 2 times 3 is 6, so the base is 6 over root 2. Done. Okay. That was hard. Just kidding. You got this, right? You can do that. Height. We gotta figure out our height. So our height, we have to plug into the square root of 9 minus x squared. So 3 over root 2 squared. So that's 9 minus 9 over 2. What is 9 minus half of 9? What's
5? Half of 9.
half of 9? 9 minus half of 9 is just half of 9. Okay. So this is just square root of 9 over 2. What?
Oh.
It's just 9 minus what, half of it? So you get the other half. Yeah. So square root of 9 over 2 is just 3 over root 2. So our dimensions are 6 over root 2 by 3 over root 2. This is the dimensions. Solid. And if we want to find the area, because what is the largest area? Area is base times height, such as 6 over root 2 times 3 over root 2, 18 over 2, such as 9. Wonderful. Yeah, so take a breath. Look what you did today. Yeah. Like 10 minutes left of class. Nope, 9. I told you these two would take the majority of class. It is what it is. Yeah. But like I knew that. That's yeah. Okay, so let's try something. Did I give everyone a practice test? I don't know why I have one extra.
Yeah.
Okay.
Wait, was that on Thursday?
Yeah.
Did you get one?
Because I left them.
It's probably you. Yeah. Oh, that's it. Okay. Yeah. So I'm gonna hand out the optimization worksheet. Ooh. I realized we already did number 1, so we just won't do it. But we can try number 2. Maybe. Do I try a different one? Maybe I should do the other one first. Yeah, let's do this one first. There's really only a couple type of problems I can ask you, which is why I want to go through so many together, because then they're going to be just like the ones here. So I want you to read number 1, try it out. Make sure you bring this to class on Thursday. We'll finish it, and then I will give you, I have more problems to do. Just so you know, the solutions for this are real ones. But I want you to try number 1. Okay, read number 1. See if you can give it a shot yourself.
Oh my god. Oh my god, my finger. My stamps. It's like
Oh, wait, we're doing number 2.
Number 1. We're doing number 1. Number 1. Hannah, work on number 1.
Is it saying x is the whole from like 0 to 1?
Just like I'm gonna open it up. Okay. So the figure below shows a rectangle inscribed in an isosceles triangle whose hypotenuse is 2 units long. What is the largest area the rectangle can have, and what are its dimensions?
Is it saying that x is like from 0 to 1?
What do you mean?
Just, like that point.
Oh, it's just saying like, oh, I'm X units over. Yeah. Okay. Okay. So if this length right here is x, what's the total length across? 2x. Okay. And then I know that
I thought 2 was from the hypotenuse of the triangle.
What?
The hypotenuse of the triangle?
The length of the hypotenuse is 2 units long. So this whole length right here is 2, but like the length of my rectangle is 2x, because I don't know exactly how far over I am x-wise.
So the domain is 0 and 2.
What?
If the domain is 0 to 2.
0 to 1. Because x can be from 0 to 1.
Oh, okay.
So then the base be 2
Okay,
minus
so first I want to discuss the y. Okay, I just want to how do I find the height? Here. The height is y. I know the equation. Do we know the equation for this? Okay, so this is an isosceles right triangle. Isosceles right triangle. We know the hypotenuse is 2. What is the... If this is 45 degrees, and this is 45 degrees.
It's x over root.
Okay.
Okay, so if this whole length across is 2, let me show you. This whole length is 2. What is this height right here? If this whole length is 2, that means that this length is 1. And if this is an isosceles triangle, guess what? This angle must be 45. This angle must be 45. If this length is 1, guess what this length must be? 1. Oh, okay. So I know that this point is at 0, 1. I know that this point right here is 1, 0. This point is negative 1, 0. Because it's a 45-45 triangle. Right? So the triangle that's like this, total length across 2, this length has to be 1, which means this length is 1. Okay. So I know what this the equation for this side length is. What's the slope? Negative 1, right? Because we're going from 0, 1 to 1, 0. The slope is negative 1, and my y-intercept is 1.
So for these different questions, what we put in before, your height is just
Because I'm inscribed.
equation for whatever is.
There's literally like 3 or 4 different problems I can ask you about. I can have something inscribed in another, just like this problem, and the one below it, and the third example we did in class earlier. Then number 3, if you flip this over, it's about a box. You can do something with a box. So it's like the second example we did today. Well, right? I can ask you about a box. I can ask you about two numbers added, subtracted together. Yeah, there's not many problems I can really give you right now. There's really only 3 types of minimize maximizing problems. So, okay, so we know the height. We figured out the equation y equals mx plus b. The slope is -1 because we go from height of 1, x of 0, down 1, over 1. That's our second point, so it's a slope of -1. Our y-intercept is 1 because literally it's where x equals 0. Well, x equals 0 right here. So we need an area formula with one variable. We know area is going to be base times height because this is the area for our rectangle. So our base is 2x. Our height is -x plus 1. And then we're going to finish this next time, but then you just have to, right, multiply it across, take the first derivative, find the critical points, and then we'll have our x value, plug in, find the dimensions, and then find area. So this is where we'll start next time. So bring this with you. We'll try to get through this optimization review, and then I'll have a couple more problems for us to do in class together.